Good morning, everyone, and thank you for joining us today. We will explain what an IP address is, how it works, and why it is important in computer networking. So today, we're going to demystify a piece of technology that is absolutely fundamental to the internet, the IP address. We're going to tackle this using what we're calling an onion model. We'll start with the device right in front of you, and then peel back the layers one by one, from your local network all the way out to the global internet. So let's get right into it. So here's what we've got on tap. First, we'll hit the absolute basics, what an IP address even is. Then we'll unravel that common point of confusion, the idea of having two addresses, public and private. From there, we'll look at the incredible translator, NAT, that lets your home talk to the world. We'll also cover how you get an IP address in the first place, look ahead to the future with IPv6, and wrap things up by talking about the huge challenge of securing this entire global system. All right, let's jump right in at square one. To get us started, what exactly is an IP address? That's the perfect place to start. At its core, an IP address is really just a unique numerical label for any device connected to a network. The best analogy is a mailing address for your computer or your phone or your smart TV. Without these addresses, the little packets of data that fly across the internet would have no idea where to go. They'd just be lost. It's the system that makes all digital communication possible.
And what's really fascinating is that this one number is doing two critical jobs at the exact same time. On one hand, it's a unique identifier. It's like a name tag that says this specific laptop. But on the other hand, it's also a location address. It gives routers a clue about where that device is located in the grand scheme of the network. So it's both a unique ID and a kind of map coordinate, all rolled into one.
That's a really clear way to put it. But you just said it's a unique address. And that's something that I think trips a lot of people up, because you often hear that you actually have two of them, a public one and a private one. How does that contradiction work? Right. And this is where we peel back that first layer of our onion, your private local network. Everything inside your house. Every single one of your devices, your laptop, your phone, all of it gets a private IP address from your home router. This address is only for talking to other devices inside your house. And for anyone who's curious, you can actually see this for yourself. On a Windows machine, just pop open the command prompt and type ipconfig, and you'll see that local address. Now, for that next layer of the onion, the public internet. Your internet service provider, your cable or fiber company, assigns your entire home one single public IP address. This is the address that the rest of the world actually sees. So as far as any website is concerned, your laptop, your phone, your tablet, all their traffic is coming from that one single public IP. And yeah, as the slide says, the dead simple way to find it is to just Google, what is my IP? So you might be wondering, wait a minute, how can my router be 192.168.1.1 and my neighbor's router have the exact same address without everything breaking? Well, it's because the standards body, IANA, very cleverly reserved specific blocks of IP addresses just for private use. These ranges are officially designated as non-routable. That's basically an instruction to all the major routers on the internet to just ignore any traffic from them. It's just like an internal office phone extension. It works great inside the building, but it's completely meaningless out on the public network.
Okay, that clears things up. But that just leads to another huge question, right? If all my devices have these private, internal-only addresses, how on earth do they all communicate with the internet using that one single public IP? How does data from a website get back to the right laptop and not my phone? And that is where the real magic happens. The solution is a process called Network Address Translation, or NAT. Your home router acts as a sort of digital receptionist for your whole network. The best analogy is an office building. The building has one main street address. That's your public IP. But inside, it has tons of different office numbers. Those are your private IPs. NAT is the receptionist who sits at the front desk and makes sure a package from the outside world gets to the right person in the right office.
Okay, so let's walk through exactly how that receptionist does its job. Step 1, your laptop sends a request out to a website from its private IP. Step 2, your router grabs that request. It swaps out the private source IP with its public IP. And this is the crucial part, it also attaches a unique port number. It keeps a little note of this swap in a translation table. Step 3, the website sends its response back, but it sends it to the router's public IP and that specific port. And finally, step 4, the router looks at the port number, checks its table, finds the match, and says, this one's for the laptop, and forwards it along. That use of port numbers is technically called port address translation, or PAT, but it's the secret sauce that makes the whole system work. And to get a little deeper into the weeds, which is always fun, not all NAT is created equal. The specific type your router uses can have a huge impact on things like online gaming or peer-to-peer applications. A really strict type called symmetric NAT creates a totally new port mapping for every single server you talk to. This makes it super hard for two people to connect directly. On the other hand, you have more permissive types called cone NAT, which will reuse the same mapping, making those direct connections, which are vital for gaming, much, much easier. This is fascinating stuff. So we've got the what and the how for managing IPs, but what about the where? As in, where do these addresses even come from in the first place? How does my laptop get an IP when I connect to Wi-Fi? I guess that brings us to the difference between static and dynamic assignment.
Yeah, for almost all of us, almost all the time, it's completely automatic. And we have a protocol called the Dynamic Host Configuration Protocol, or DHCP, to thank for that. When your device joins a network, it basically just shouts out, "Hey, I'm here and I need an IP address." The router, acting as a DHCP server, hears that request, looks through its available pool of addresses, and leases one to your device for a certain amount of time. That whole back and forth negotiation is what we call dynamic IP addressing.
And this table really lays out the trade-offs perfectly. Dynamic IPs, the kind you get from DHCP, are fantastic for consumers. They're automatic, they're efficient because your ISP can reuse them, and that keeps costs down. Static IPs are the opposite. They're permanent and manually configured. You'd never want one for your phone, but you absolutely need one for something like a web server or critical network printer that has to be reachable at the exact same address always. The trade-off is that they cost more and require manual setup. So this whole system, NAT, DHCP, private addresses, it has powered the internet for decades. But it's also, a system built on a foundation from the 1980s. And the problem is, nobody back then could have predicted the sheer explosion of the internet. It created a problem of scarcity they just never saw coming. We literally started running out of addresses.
That's exactly right. The original system, which we now call IPv4, is built on a 32-bit address space. And the math on that is pretty simple. It gives you a hard cap of about 4.3 billion unique addresses. In 1985, that must have seemed like an infinite number. Today, with billions of people who each have multiple connected devices, it's a massive shortage. That well is completely dry. So the solution is the next generation, IPv6. And it's not just a small upgrade. We go from 32 bits to 128 bits. The resulting number of addresses is, well, it's just mind-boggling. 340 undecillion. I mean, the number is so big, it's hard to even wrap your head around it. To put in perspective, that's enough IPs to assign one to every single atom on the surface of planet Earth. So the bottom line is, address scarcity is a solved problem.
But here's the really important part. IPv6 isn't just bigger, it's smarter. The packet header in IPv4 was kind of clunky and had a lot of fields that slowed things down. IPv6 completely streamlines it. They threw out unnecessary fields, but the real genius move was getting rid of the header checksum. In IPv4, every single router along a packet's path had to recalculate this checksum, adding delay at every hop. IPv6 basically says, let's trust the protocols higher up to handle error checking, and that makes routing on the internet's core backbone so much faster.
Okay, so we've got this incredible next-gen system with basically infinite addresses and a more efficient design. But it's a global system. And that raises the question of security. How do we make sure that all this traffic actually gets where it's supposed to go? How do you prevent someone from maliciously redirecting or spying on it? That is the million-dollar question, because the internet's fundamental routing protocol called BGP was literally built on a handshake agreement on trust. Big networks simply announce to their neighbors, hey, I'm the path to get to this block of IPs. A BGP hijack is when some bad actor, or even just an engineer who made a mistake, falsely announces, no, send that traffic to me. And just like that, they can divert unbelievable amounts of traffic, causing huge outages, or, even worse, spying on everything that passes through.
So down at the individual packet level, we have a set of tools called IPsec to protect data itself. You can think of it as having two main components. First, you've got the authentication header, or AH. That's like a digital tamper-proof seal. It verifies who sent the packet and proves that the data hasn't been changed in transit. Then you have ESP, the encapsulating security payload, and that's the encryption part. It scrambles the actual contents of the packet so that even if someone intercepts it, it's just unreadable garbage to them.
And to solve that bigger, fundamental trust problem with BGP, the whole industry is now rolling out a system called Resource Public Key Infrastructure, or RPKI. The easiest way to think about it is like a cryptographically secure deed or permit system for IP addresses. An organization creates a digitally signed record, a route origin authorization, or ROA, that basically proves, yes, we own these IPs and we are allowed to announce them. So now, when a network sees an announcement, they can check for a valid permit. If there isn't one or it doesn't match, they just drop the route. It's a huge step forward in preventing those hijacks.
Wow, so we really have peeled back that entire onion today. From the private IP on your laptop, through the cleverness of NAT, into the massive new world of IPv6, and right down to the cryptographic bolts like RPKI that are trying to hold it all together. It really is an incredible system. Which leaves us with this final thought. Is this push for cryptographic validation the ultimate solution for securing our global internet? Or are new, unforeseen challenges already on the horizon? Thank you so much for that fantastic explanation. Thank you so much for watching. If you enjoyed this, please subscribe, like, and share, and don't forget to hit the bell for more from TechAI and Beyond.